Alright, so I think I'm going to work on part 2 of the SCL videos. Um, the ultimate goal is to do like the factory I/O project assembler, but we're going to get there in time. So in the last video we made a debounce ladder block and a debounce SCL, and probably the next one is we're going to focus on like handling Boolean bits. And sometimes you'll get like, you'll want to know, you'll check against a push button and you'll want to know when somebody presses it, when they're holding it, and when they're releasing it. So you'll have a series of one shots that you're doing this with. Or like a conveyor, you might want to see, when your part is moving down the conveyor and it comes up to the sensor, or when you're at the sensor, or when the part has left the sensor. So, like, if you're moving this part down this conveyor and there was like an inkjet printer or something like that, you might say, whenever it arrives at the sensor, we turn it on, and as it's leaving, we unlatch it, to run this printer. So, let's see. So if we wanted to write that in ladder, I don't think I said this in the previous video, but so we're using TIA Portal version 17. Let's see, I'm going to make a new FB function block, and we're going to call it bool state ladder. Write this in ladder. So if we go to our interface, we're going to have input, data type bool, and then we're going to have a output of a rising edge. We're going to have an on, and we're going to have a falling edge. And then, so let's do our logic for our rising edge. So we're going to say actually that's okay. Now, because we're doing the edge of a Boolean input, we need a memory bit to store this against. So I'm going to make a structure in our static memory, and we'll do a rising edge and a falling edge. So we'll go edge, data type structure, and a person doesn't have to do it this way. I'm just doing this maybe to help keep it a little bit more organized for myself. This network will be easy enough. Okay, so network 1, we're looking for the rising. We're going to find the rising edge of our input. We're writing that to our output rising edge. Network 2, we're doing just remapping the input to on. And then network 3, I'm going to do falling edge, and we're going to say so now we're comparing our input against our falling edge, and then we're going to write out to falling edge. Okay. So let's write one up like this in SCL. So we're going to add a new block, function block, SCL, call it bool state SCL. And put these side by side. Input. Same type, I'm going to put our structure in here. All right. All right, so our first one's our rising edge. So I'm going to click the rtrig instruction, drag it over here. We're going to do a multi-instance. Yeah. I might not have to do my, it's been a minute since I've had to do it. I guess I wouldn't have to do my static memory bits. Rtrig, yeah, we'll go with that name. Oh yeah, okay. So we're going to take and get rid of my edge structure. I guess we don't need it. Let's talk about what this rtrig actually is. It looks to me like it's an FB that they've already written and packed here into the library here. Clock is what you're actually checking, what Boolean bit you're checking, and then you don't have to define your memory bit because they're stacking it into the static already. And then Q is what you're using as your output. Now, and then maybe we'll take a second and talk about what, you know, if a person wanted to write one from scratch, what that involved. Like, when your edge detection, you take your edge and then you have your previous state. And your rising edge is when your input's positive, but your previous state was negative. And that's when you would say, like, rising edge equals input and not previous state. And then in the next line, you're going to put previous state equals input. So what you're doing is you're looking for a change each scan to see, you know, the very first scan that you got a true input, or, you know, but they already write that into here and pack it in there for you. And it's the same thing they do in ladder logic too. Okay, so we got our rtrig instance. Our next variable here was on, so this is just a plain assignment. We're going to say on equals, or assign, input. That's easy enough. Okay, and now we're going to do our falling edge. ftrig multi-instance, yeah, we'll call it ftrig instance. Okay, we're going to take our input, and then our output's going to go to falling edge. Okay, I'm going to turn off these set points, I don't need that. And that's it. So let me compile these and look at the difference between the two, or I guess we'll call them two. So we're going to take, we did our ladder before, bool state ladder, single instruction, sure. We're going to, from our previous one, take this ladder debounced input, pack it into here, and then let's what was that? That was 0, 0, I know, 0, 0, 0, 1 for our, yeah, M01. This was M02. I guess we'll stack more on top of it. Let's call this ladder rising edge. We'll define the tag, global memory, and we'll just do the next bit that's available. Ladder on. Okay, now let's do same thing with SCL, bool state SCL. I'm going to take that one and pack that into here. See, SCL, right, oh, typo. I'm going to define this tag. Let's make a new tag for this too, SCL, falling edge. Alright, compile that, and let's download that. Maybe we'll get the opportunity, we'll put a trace in here and check against our rising edges and falling edges too. I don't remember from the last video, yeah, we put a watch table in here. Alright, so if I write this raw input true, let's send it. Remember we had them running through our debounces from the previous video. Okay, yeah. And then ladder on and SCL came on. But we do have, which we don't see it because it blasts out real fast, but our rising edges and our falling edges. Let me go back to my OB1. I put the falling edge in there, didn't I? Ladder, falling edge. Oh, I didn't. I made that a local value, didn't I? Can I rewire that tag? Let's do this. Let's break this. See, I made that a temp instead of an mbit. So I need to get rid of the hash. Then we'll define the tag. See, last time I forgot. I clicked local temp. I didn't click global memory. Yeah. We'll add that into our table too. That address was M1.0. Yeah. Okay. Okay, so when I write this to false, all of these should kick back off after, how long did we do? After 3 seconds. We'll send it. Yep, there we go. Okay, so now let's see if we can get our trace on and then see if we can see that edge. Add new trace. We want to record sort that. Come on, computer. I guess I'll put these side by side. That watch table, and I got my addresses handy too. So I want to do, I think of a good way to do this. Hey, sweeties, go to the sunroom. My dogs are wanting to talk to me. I'll play with them in a little bit. Actually, let's do, because we don't necessarily want to track a gazillion scans. We're going to do M0.1 ladder debounced input, and then we're going to check M0.3, M0.4, M0.5, and then M0.6, M0.7, M1.0. Okay, we want to record every cycle. We want to do 2,000 cycles. If we're just doing the edge detection, we only need to do maybe 100 cycles. Trigger mode, trigger on tag. We're going to trigger on our ladder debounced input. And then let's do pre-trigger of like 25 cycles. Okay, let's see, I think this is transfer to device. And then we want to start recording, waiting for trigger. Okay. when I send it, yeah, okay. So let me make this full screen. So I turned on our raw input, and remember it took like 5 seconds to debounce and turn on. So once that debounced input came on, then our rising edge came on for one scan. See, the same time our on came on. And we gotta take my word for it, but I promise you the ladder debounced input we checked in the last video works the same as the SCL debounced input, even though that's what's driving these SCL bits. But it kicked on for the same one scan, and then it's on the whole time. So let me go back to I wonder if I can I forget to write that different bit in there. Not defined. Define that. Well, Brog snacks. Is our microphone still working? Might have had a short technical difficulty. Rising edge on falling edge. Then we had edge, struct. We had rising edge, falling edge. Okay, so rising edge equals input and not edge dot rising edge dot rising edge equals input, and then we have on, same thing as the other, equals input, and then we have falling edge equals not input and edge dot falling edge, and then edge dot falling edge equals input. So, and this is how all of your like one-shot stuff works. So we're taking the rising edge and we're saying that is that's equal to our input and not our rising edge. And then we take our rising edge and we rewrite it based upon input in the next scan. So it runs, so say your input's 0 right now, on your first scan. Okay? So it's going to say rising edge equals 0. Okay, nope, can't do. You already screwed it up. It's wrong. So rising edge is going to be false. Then this line 2 is going to say rising edge equals input. So rising edge is going to be 0. This right here, this edge dot rising edge is going to be equal to 0. Next scan input, let's say our input is 1. Okay, rising edge equals input, which is true, and not edge dot rising edge, which will be 0, but we're inverting it. So you got 1 and 1, which equals 1, right? When you and 2 ones or you and 2 trues, and you get a true. So now our rising edge is true. Edge dot rising edge equals input. So now edge dot rising edge is going to be true. Next scan coming around, let's say our input is still 1. It doesn't matter what it is, but if it was, okay, so if it was 0, this would be false, so that would kick out rising edge. If it was true, true, but this is also true from the previous scan, and now you're doing an and, or this needs to be 0 or false, so true and not true, well then that's going to make that false. So that's how you get your single blip. So let's compile that. Now will this show up in program info, or do I need to call it? Yeah, that's more like it. See, now we're using half of the work memory doing it like that. But a person has to write this code, kind of on their own. And I bet, although I don't have the ability to unlock it, but I bet if you go under bit, like if you could open up this R trig and F trig, that's what these things are doing inside them. Alright, well, so we're going to use, if you get a chance to look at the factory I/O project for the assembler, it has like a conveyor with lids and a conveyor with bases, and it has a in-feed sensor on the lid conveyor, and the way they lay out their sensors and stuff, we kind of need the falling edge of the lid conveyor. So, we're going to use that to pack that in. And then on the base conveyor, same thing, we need the falling edge of the in-feed of the conveyor, and then we might need the rising edge or the falling edge of the output conveyor. And then some of the actuators in factory I/O, they do stuff like saying, like I think there's a little gantry style crane or a single or two axis little crane to move the lids over to the bases, but it doesn't have like a limit switch on each end of this axis. Instead, it just has a bit that when the axis is moving. So a person needs to write logic to say, I'm looking for the falling edge of movement and then what direction it was headed into, and that's how I'll determine whether this was extended or retracted. Alright, well, thank you for watching. I think this is going to be the end of the video today. Hope you have a good day. Bye.